welcome to the second part of the lecture on using this gradient descent-based techniques for addressing the graph-based slant problem. We just very briefly repeat what I was telling you last week. So it is one alternative approach to minimize the error in a network of constraints, and the key idea of this stochastic gradient descent was to randomly pick one of those constraints and then try to deform the graph locally, it's just a small subset of the nodes, so that the error that is introduced by this single constraint which was selected is minimized. Which is kind of the key idea. And then one typically samples those constraints during the iteration, so one constraint typically in a random order, and then try to minimize the error introduced by this constraint. The problem is if I solve these small sub-problems, it can happen that one constraint tells me the node sitting over here should move in this direction, the other node, other constraint says it should move in the other direction. So we may have constraints where the solutions contradict each other, and therefore one introduces a so-called learning rate, which decreases over time and which is linearly multiplied with the update. So this value tends toward 0, and so in the hope of finding a good equilibrium point. So this is one illustration. We have this network over here. We select this constraint that we want to minimize in this step. So we check which nodes, in this case these are all nodes, which need to be updated so that this node moves down here. So we move a little bit in this direction, update all the nodes, we iterate that process, and hopefully we'll end up in the configuration that we want to achieve. And if you look to the individual update rule of the stochastic gradient descent, it was kind of this formula which takes into account in which direction should we go. That was a residual. What is the uncertainty associated with this edge, and how do we transform that into the corresponding, I don't want to call it reference rate, but parameterization, so how the nodes are parameterized. The key problem with this update rule here is that the system doesn't know about the 3D rotations. This was kind of the main, or one of the drawbacks that this stochastic gradient descent comes up with, that it treats the state space as a Euclidean state space, so it doesn't know about the angles which are involved. Especially if you have 3D rotations, that means you have more than a single rotation. You have the problem that you can, that the multiplication of this rotation matrix is not commutative, so you cannot change the order. If I first do a rotation around the x-axis and then a rotation around the y-axis, if I do that the other way around, I come up with a different solution. And that's one of the problems that the stochastic gradient descent-based techniques encounter if they just apply the standard update rule. So the key idea here was, can we come up with a better solution for distributing the error, which explicitly takes into account that we have 3D rotations in here. And can we just, let's say, formulate an update rule which is, let's say, in the spirit of this update rule, but which takes the 3D rotations appropriately into account. And so we had this situation over here. As an example, we have a sequence of nodes pi to pj, and we know that we have a constraint or a measurement which tells me this node pj should actually be here. So it's moved and rotated. And the idea, so at least how this approach does it, is it first corrects the rotations so that the rotation of this node and this node over here are the same. The goal of this single update. And then it does the translational error. And we were kind of stuck in the question of how should we actually distribute the rotational error along that chain so that the rotation of the node pj is actually rotated in a way that it corresponds with this constraint. So this was the question we were trying to answer. And so we formulated in that way. We have a number of rotations. These are relative rotations between the nodes. So there's no rotation at all. These rotation matrices would be the identity. So the nodes are not rotating against each other. And so the R1 to Rn, that's a current configuration. So the current configuration we have. And we have the additional information on matrix, rotation matrix B here, which comes from the constraint, which tells me this node Rn should actually be rotated according to Rn times B. So it should end up over B. So we have here n plus 1 rotation matrices, and we want to rearrange that so that we have n rotation matrices, so that the rotation which is introduced by this constraint B is distributed over the individual rotations. So in the 1D case, which actually can be done quite simple. If you have just one single axis of rotation, which is identical for all the rotations, let's say you have 10 nodes, all look straight. You say the last node should be rotated by 10 degrees. That's what my constraint tells me. How should I distribute this rotational error of 10 degrees over these 10 nodes so that the squared error is minimized? This is quite easy. It's just if I have 10 nodes, let's say all the constraints have the same information matrices, have all the same uncertainty, then it would simply be, let's rotate every node by 1 degree. So I rotate every node by 1 degree, so the last node will be rotated by 10 degrees. That's easy in 1D, in the 2D world, where I have just one rotation axis, because I have only a single rotation, axis of rotation. If I have, however, multiple axes of rotations, which happens in 3D, I have also 3 rotation axes around the x, y, and theta, I can't simply, let's say, divide the individual angles and let's say I rotate 1 degree around the x-axis, 1 degree around the y-axis, then again 1 around the x, 1 y, 1 x, 1 y. This won't work because they're not commutative, these rotations. And so the question was, how can we actually compute this r prime 1 to r prime n given this information r1 to rn and b? That's our goal. That's what we want to do. We want to find a way to distribute the rotational error. So I decided to do that on the blackboard so that you have an easier way to interact with, so that you see how this thing is derived. So we have our situation where we have our nodes, and we have this rotation over here. So this was B, Rn, R1. We want to transform that to so that this is Rn prime, R1 prime. We want to compute this R1 prime and Rn prime, this is the values I'm interested in, given this R1 to Rn and given the B. So everything every rotation matrix which is called R here is a relative transformation between two nodes. Whenever I use the matrix A, it means in the global reference frame, the reference frame of the world. I, however, simplify my problem. I can do that without using generalities. I put this node in the center of the reference frame. This just makes some of the iterations easier, but exactly the same applies also if this is not false. Okay, so I have these rotations. Sorry, I have these rotations. I want to compute these rotations over here, and I want to do that in a way that I perform all these rotations, that kind of the increment, the error I add to that, around a single axis of rotation, because then I can easily distribute the error if it's a single axis of rotation. So from these additional rotation matrix, I want to compute one single axis of rotation and rotate around this axis. So what I know is that An prime, so this is the rotation of the nth node after the update, this guy over here in the global reference frame. So in the reference frame of this node. This is given by An, the one we had before, times B. Right? That's the rotation I had before, and there we're end up with, so it's Rn times An times B. Right so far?
These are the rotation matrices?
These are the rotation matrices, yeah.
All of them?
What do you mean with all of them?
Yeah, R1 to Rn generally.
These are all rotation matrices, R1 to Rn.
On the left-hand side, we have R1 to Rn, and then B.
Yeah.
Right there.
Mm-hmm.
And on the other side, we have R1 to
Rn.
prime.
So this is kind of what the constraint tells me.
Yeah.
So this guy should be here.
And so on the right-hand side, we have one less rotation matrix.
Exactly, one rotation less. Yeah. So here I have n rotations, and here I have n plus 1. So this is what I know what I have. And I want to express this, as I said, by one rotation around one single axis. And this is then done by the rotation matrix Q, which represents this single rotation around one axis, which is now multiplied from the left-hand side because it's the rotation. You can see that's a rotation of the whole global reference frame. This rotation axis is the same for all rotations I actually conduct. Okay. And we have now that this guy, given that this node is the center of the reference frame, is R1 to Rn prime, right? And this one here is R1 to Rn. Okay. And what I want to do now is I want to find a way to distribute, to say this Q is equal to Q1 to Qn, so that I can split up this matrix into n small rotations, where the matrix Q1 rotates A1, the matrix Q2 is applied in between here, Q3 is applied in between in here, so that I end up with these relative rotations. Is that clear? Okay. If not, ask me.
Could you say how you get from A and B? So you've got the left-hand side, and then you get to the Q. How would you calculate that Q?
That's actually the key trick on how to do that. That's what I'm going to derive. So,
okay.
So I will tell you how I can compute the Q's now with this slurp, which is actually this interpolation, and then you can actually show that, given you do it in that way that I show you, that we actually end up with the solution you want to come up with. So we have or briefly introduce the slurp. So, yes, please.
So it's delta. Is it delta? The triangle n, is it?
Triangle n.
This is
A.
N. Sorry, yeah. Is it one vector now? Or one
this is a rotation matrix. It's all rotation matrix.
So it contains the sum of rotations of all from 1 to n.
So An is the rotation of the last node in the global reference frame. And given that I set the center of the reference frame at the first node, it's given by the chain, by chaining up the individual rotations. Because if the first node wouldn't be the center of a reference frame, I would have another rotation sitting here in front. This is just for the special case that the first node sits in the center of the reference frame. If I then want to compute the rotation of one node at the end of the chain, I just need to chain up all the individual rotations. Any further questions? I can clarify here at that point. So I briefly talked about the slurp, and I think in the exercises, Nicola and Ryan also talked about the slurp. For me, the important thing here is not actually how the slurp is exactly done, but what the properties of the slurp are. So that the rotation axis stays the same. If it slurp, is all these properties clear, or should I repeat them again? Repeat? Or okay. The thing was, if I have a rotation, just give them whatever, rotation matrix C, just have no confusion here. And this rotation matrix C is equivalent to the slurp of C and a value of 1. So the value of 1 here, the rotation stays the same. The identity is a slurp of C and 0, so there's no rotation. And what I typically use, I use slurp of C and a scalar value U, which typically has values between 0 and 1. This can be used to kind of break down rotation to into the sequence of small rotations. As I said, in 1D that's trivial, versus just one angle, so I can linearly divide that. But the slurp tells me how I do that in actually 3 dimensions when I have this different rotation axis. And the properties I have in the slurp here is that the axis of C is identical to the rotation axis of the slurp of C and the value U. So if I apply the slurp function, the rotation axis doesn't change. It's a rotation around the same axis. And U times the angle of the rotation, so just how much I rotate around this single axis of C is equal to the slurp of, angle of the rotation of C and U. So if I say, slurp, angle of rotation of the slurp of CU. So putting a value here, for example, about 0.5 in here, means that I conduct the rotation around one axis, but only half of the rotation. So you have this linear dependency here. So this is therefore slurp is also this is the abbreviation for a spherical linear spherical linear interpolation. Sorry, I forgot exactly what that abbreviation is. And so these are the important properties. These are the properties we're going to use now. So the slurp maintains the rotation axis, and with this real value, scalar value u, I can tell about how much of the rotation angle I'm rotating, given that the axis stays the same. So something which is trivial in 1D, we have just one rotation angle. Something which is non-trivial if I have more than one rotation angle. And the reason why this is non-trivial because I cannot it's a non-commutative operation, the rotation. So it makes a difference if I first rotate around an axis 1 and then around an axis 2, or if I first rotate around an axis 2 and then around an axis 1. That's the reason why this makes a difference. Why this is non-trivial if you have more than one rotation axis. Okay. So we have these guys. And the question is, how do we now compute these QKs? I'll tell you now, one way to compute them, a smart way to compute them, is say, this is a slurp of Q, and the value U corresponds to K minus 1 transpose times slurp of Q of UK. So that what the U's tell me, so to go from the beginning to the end, so from 1 to n or from 0 to n, I start with U, 0 is 0, there's no rotation, and UN is typically 1, because then I did the complete rotation. So when I come down. So these values, these UKs, so let's assume the case where all the constraints along the path have exactly the same uncertainty, there's no special thing involved, then these UKs would be k divided by n. So if 10 rotations is 1/10, 2/10, 3/10, 4/10, and so on. Okay. So what this does is, let's say we have a rotation around 10 degrees and we break it up into 10 individual rotations. This, if we have k equals 6, for example, then this would be 0.6, or 6 over 10, and this would be 5 over 10. So what I do is, and this is a transpose, so it inverts this rotation. So it would be 6 degrees in one direction, 5 degrees backwards. So it would end up in a 1 degree rotation. And that's exactly what I want to do if I want to break a 10 degree rotation down into 10 steps. So I have these two slope functions in here because you can see the slope is considering the whole rotation. But I just want to make the small increments. And therefore, I have the slurp with UK minus 1 here transposed, which rotates already in the backwards compared to the original this function, because it's not transposed. So I'll go kind of k steps in this direction and k minus 1 step back, so I have exactly one step. This is exactly one step I want to come back. Is that kind of, is that clear?
I think I missed it. Why don't I just choose my u in the correct value in the first place?
I haven't talked about how I choose k right now.
Yeah.
So k typically depends on the uncertainty which is associated to the constraints. So if I have a constraint which I'm very certain about, I don't want to introduce a big error here. If I have a constraint I don't know much about, I may have a bigger UK for that. But if you assume them all to be equal, just keep it easy. You want to have then you will have a uniform distribution of these fragments of the angle around the all nodes. So if I have 10 degrees I need to distribute. If all have the same weight and I'm not more certain about one constraint, it would be 1 divided by 10 for every, or 10 divided by 10 for every rotation.
Well, what I mean is, if we know that we're going to take 6 steps one direction and 5 steps back,
yeah.
Why do we not just make 1 step?
Okay, yeah, that's exactly what you want to do, but the problem is you can't compute it. How to compute that?
No, we have equal, we know UK. No.
You could, I mean, you explained already why we don't do this, but you could do, if you have 10
okay, you could do this equal to
0.1, 10 times will get you there.
Exactly.
But you don't want to do that because you don't want to do all this same amount.
You could probably do the same if you go for a slur Q and then UK minus 1. That should actually be worked out in the same way. That should work exactly in the same way. If you do it this way, the derivation becomes easier, which I will do now. Because then you can nicely see how terms cancel out again. But if you will do it that way, implement it, should be exactly the same. Okay, so where are we right now? So, given what I know here, what I can say is that AK prime, so this was the, as a reminder, this was R1 to K prime, so it was a chain of relative rotations, the global one. And this should be Q1 to K of AN, AT. Right? So if I have the second node, say A2 prime, which I'm interested in, this should be Q1, the first correction of the first node, and the second one, and then these AK. Okay, so. One relative rotation now, I can express as A K minus 1 prime transposed A K prime. So these are the global rotations. Maybe just put that around so it becomes clear what I transpose. So this is the absolute rotation in the global reference frame of K. And of K minus 1 transpose exactly gives me the relative transformation to go from K minus 1 to K. So I can now put the function I have in here, so this equals to Q1 to QK minus 1, AK minus 1. So this is now not primed. And the same replacement here, Q1 to QK, AK. Yeah, exactly. And now I split up these terms, so if I transpose this, I can transpose the individual matrices and the order changes. So this becomes AK minus 1 transposed, QK minus 1 transposed, Q1 transpose times Q1 QK AK. So if I look to the inner blocks here, this is the identity. And the second one here, again gives the identity. So I continue with that, only the QK remains. So that's A K minus 1 transposed QK. And I can actually express this now. This is exactly the same as R1 to K minus 1 transposed QK R1 to K. Of course, this was the original equality we had. And this equals to RK prime. So what I have now in here, this is the quantities we were looking into. What are the relative rotations? What need to rotate the individual nodes along that chain that the error is distributed. This quantity is known. This quantity I know how to compute with a slur. And this quantity is known. So I'm now able to compute these terms over here. Because this is known, this is known, and this is known. So I agree that the way I introduced the slur appeared a little bit magically. Just said, that's a slur, that's how I compute my Q. But the important thing is, if I define the Q in the way as I did it here, I actually get exactly the properties that I want. That I have one single rotation around one single axis. I can actually break that up so that I have, if I distribute about n small rotations, I get exactly one nth on every one nth update on every node. Is that clear what happened? So if you're if you're not considering angles, you let's say consider distances, it's much easier to understand for us. You say I have a node here, it should be over there, so it should move, let's say, about 1 meter, and I have 10 nodes which are associated to in that chain. We typically say, okay, move this guy over here, where it should be, by 1 meter. The second node I move by 90 centimeters, the next one by 80 centimeters, by 70 centimeters, 60 centimeters, and so on. Because this will introduce an error of only 10 degrees along each link or each constraint. And if I'm interested in minimizing the squared error, the best thing to have is have a uniform distribution of the error on the individual quantities. So it's very clear how we do that for distances, because it's linear, so we very well understand distances in our brain. It's just the linear scaling of all those nodes. And the trick is, this is the way you have to do that for rotations. If you've done exactly the same way, one node is pointing over here, it should point over here, and there's a chain of nodes connected to that. If this guy should point over here, by which should we rotate the individual ones so that we actually end up in distributing an error so that the squared error is minimized. Again, our brain is still able to do that for one single rotation around one axis, but the problem is if the error is not the rotation around one axis, but on the x-axis and the y-axis, then it becomes complicated, and I need a way of bringing that back to a rotation around a single axis, which is now not the x, y, or the x anymore, but some arbitrary axis in space in order to distribute the error. Any questions about what I did so far? Good. So let's not skip over the slides a little bit, because this is basically everything that you hear on the blackboard you actually find here on the slides for your records. So you have the individual steps, you have the property of the slur, and the way you actually arrive at it, and then we did it for K, you can do it recursively for all the individual blocks over here. So, so this is the resulting update rule you can see over here, and that's actually the update rule that we actually derived from the blackboard. And one of the important properties in here is that that the change which is introduced, so the delta, which is added, the difference between Rk and R prime k, so the small increment are added, that this is bounded by the angle of the qk. So the error that I introduced is bounded by the angle of the individual qk. So that's kind of important to note that I just make, if I want to distribute an error, let's say 10 degrees around the individual nodes and split it up in equal pieces, the errors I introduce are, in the way I do it here, not bigger than 1 degree. So it's not that I tweak them here a little bit, those angles, and somewhere else I introduce a very big error. That's the important property that I need to, if I'm interested in minimizing the squared error. So that's the important thing. So if I do a little tweak here, I'm sure that I don't add or introduce a big error somewhere else along the chain. Therefore, this is so valuable. So what I kind of skipped now, or actually removed that from the slide, is the way how do I compute actually these UKs, these individual values, the UK. I used the slur. So these guys over here. So if all the nodes along the graph have the uncertainty associated to all the individual nodes is exactly the same. It's typically just a uniform distribution. The problem that I have is if I work in real systems, I often do not have, I have covariance matrices which tell me I'm more certain about one dimension than about another dimension. And it's very hard to actually boil down that into these individual UKs because this is just a single scalar value, which has just one rotation around one axis, and cannot take into account the uncertainty which is associated to individual dimensions. So therefore, typically, quite rough approximations are needed in order to come up with a solution here on how to distribute the error if I have covariance matrices that are kind of weirdly shaped or non-spherical. And therefore, this approach only works well if you have spherical covariances. It can be the case that one is bigger than another one, then what you typically use, you just take the eigenvalues of the covariance matrix and say take the biggest eigenvalue and use this for scaling with the uncertainty. So if you have a covariance matrix which is very, very large in one dimension, you say, oh, about this node I will introduce or distribute a larger error than if I have a covariance matrix which is very small. And this works well if they're in spherical shape, but if they're non-spherical shape, that may introduce to significant approximation errors. But that's an approximation that this approach does. So there's quite some math involved in how to compute the UKs. I thought I'd actually skip that and don't bother you too much with that because it was anyway a rather crude approximation. So let's say if all the observations are kind of the same type and I have the same uncertainty associated to all of them, you just basically uniformly distribute the error around these individual nodes along the chain. If this changes, or if I have constraints which are dramatically different and non-spherical, for example, if I use vision, where typically can quite accurately determine the angle towards a landmark, but not how far it is away, this approach is likely to fail. Or may introduce very large approximation errors, may take very long until it converges. At least it's a suboptimal approach to choose for these kind of situations. Okay, that was the rotational part. The nice thing is the translational part is super easy. It's trivial. So the only slide I put on that. So if these are the nodes, and we're just talking here about a movement, and we say this, the constraint tells me this node should be over there. We just actually scale the individual nodes, how far am I along the chain. So this guy moves on top of that, and then if I have, let's say, 4 nodes here, this moves by 75%, by 50%, by 25%. So that's really easy to do. It's just linear scaling of the translation. So that's just the only slide I put on that. Yes, please.
Are you not using that uncertainty associated with
yes, you do that. If you have individual uncertainties, you just scale them with the uncertainty in here. But as we have the uncertainty issue with the rotations, the same. So the limitation about how to take into account the information matrix comes from the rotation. Here in this case, you could actually easily take into account that you're, let's say, more certain about the x dimension than about the y dimension. This is just by scaling it with the with your covariance matrix. You do that. You still have the limitation that you need roughly spherical covariance for the rotation, so this constraint still applies. And if they are spherical, you still need to scale it with the size of the covariance matrix. Any further question on that? Okay. So time to sum up a little bit. How does the approach work in sum? So what we do is, the key idea of this stochastic gradient descent-based approach was, as I said before, splitting up the large problem with all these constraints into a smaller problem where I pick out a constraint, potentially randomly, and then select which nodes do I need to involve in order to minimize the error introduced by this constraint. This comes from the tree parameterization that I introduced last time. The tree parameterization tells me which nodes do I need to update if I want to minimize the error on this single constraint I just picked. And then I distribute the error with the technique I explained here. So I first reduce the rotational error, and then the translational error is the same. With a few notes on how should I actually select the constraint. So if you apply a standard technique, you would just randomly select the constraint and update that. There are smarter ways for doing that in terms of computational resources that you save. And this comes from the tree parameterization. You have this tree, and if you remember, whenever you update a node on top, all the nodes at the bottom change as well because they're parameterized relatively to the parent. So it actually makes sense to select the constraints in an order that you go from top to the bottom of the tree. Because if you go from top to the bottom, an update you do on top, the nodes on the bottom are automatically updated and potentially already placed into a good solution that the update which is done on the bottom doesn't change the one on top. If you do it the other way around, you first update something on the bottom, where you change a lot of constraints, this may impact how the nodes on top may be updated. So it's typically much more effective to process a tree from top to bottom and update your constraints. You can do it much more efficiently if you do it that way. That's just kind of a side note. So it's faster if you go from the top to the bottom, but in theory you can select a random constraint and then proceed with that. Yeah. And computing the nodes which are involved in the update, so if I have a constraint, which nodes should I update? That's actually something which, as I said, is given from the structure of the tree, and that's something you can easily pre-compute, because you just need to compute the path in the tree from one node to the other node. This gives you the node which are involved in the update. So this is something you just do once, and then you kind of a lookup table and say, to update constraint I need to introduce nodes 1, 2, 5, 10, 15, and then you just update them. So this is just to do something you do as a pre-processing step. Okay, so do you have any idea about the complexity of this approach? How costly is this in terms of constraints, nodes, introduced per iteration? So how does it depend in terms of the number of constraints I have?
Per iteration.
Always per iteration. At least.
K, we have the indices K.
So I'm not talking about a single constraint, about updating all the constraints one. What's the minimum dependency on the edges I have in my graph?
N minus 1. We have n nodes and n minus 1 edges.
No, I'm not talking about nodes. We can have much more edges than n minus 1. Because we can have, the whole graph can be arbitrarily connected. But arbitrarily good. Okay, so I have a certain number of nodes, m edges in my graph. And I pick out every constraint at least once per iteration and update it. So it's at least a linear complexity I have in the number of edges, because I look at I try to minimize the error introduced by every constraint once per iteration. So it's a linear complexity just for selecting. How many nodes or how many edges or nodes, in this case doesn't matter, are involved when I update the error of a single constraint on average.
All others which are connected?
Yeah, I think you mean the right thing.
Starting from the reference up to, say, when we are ending, because we here we update the end, we try to start from the global reference frame, which is node 1, and then go to ends 1 and then update them, but we don't.
So we don't have to walk up the tree because for us just the relative displacement between two nodes is relevant. But it's not too far away.
I mean, I think that's what you said. I mean, we have that tree,
Yeah.
and now obviously if you start from top and so on, but let's say we have a node A and a node B
Yeah.
on another branch, then we need to traverse
Exactly.
these two branches.
Exactly.
So,
And this is exactly the number.
but we don't know how many there
Yeah,
is.
that's definitely true. But what we typically can do is, if we have one of those long edges, we have quite a large number of small ones, because all the neighbors which are connected, and then that's one long one. And what we can actually do, what it ends up with actually is the average path length of the parameterization tree. Sometimes it's a short path, and quick. Sometimes it's a longer path, but it actually scales linear with the number of nodes or constraints along one of those paths. We can see this kind of the average path length which depends on the parameterization tree. These are the two important properties. But I need to touch at least every constraint once per iteration, and then it depends on how the graph, how the tree is actually built up and how it actually is connected. So the complexity depends, as I said, on the number of constraints and which are involved in the value L, which is called the average path length, the parameterization tree. So it's hard to say something about L tree. You can actually plot that one against each other, and so what you see here is a log curve, which is logging the number of nodes. And this is the average path length that we obtain. So for different randomly generated graphs, up to 2 million nodes involved in here. You actually see that this value seems to be, so these are kind of millions of randomly generated graphs, an average of all of them. It seems to be somehow at least not much bigger than log n as a number of nodes. So it turns out that typically you have the path length that you experience is typically less than the logarithm of the number of nodes in the graph. This is definitely not a proof at all. Never claim that this is a proof. This is just by generating millions of graphs and just evaluating how the structure looks like. And you can actually also see that these just to give an impression why those values are typically small. Just point that out. So if you have, say you have this is your graph structure that you have. Go traverse close the loop once, and you build your parameterization tree from that. What you typically obtain in such a easy situation that you have a graph which looks more or less like a list. And then you have one constraint which connects these, and this is the element which is not in the parameterization tree. So if you look at the average path length between the nodes for which an update is done, between these two nodes it's 1, 1, 1, 1, 1, 1. And then once it's n. And if you average over them, it's to be n minus 1 times 1 plus n, which is the long one. If you want to compute the average, if you have n constraints in the game, it's something which is similar to 2n by n, which is 2. Because we have n minus 1 of these individual constraints, plus n, which gives me 2n minus, it's actually 2n minus 1. This is 2n minus 1 divided by n, and this is smaller or equal than 2n to n, it's 2. So the average path length in this situation is 2, it's constant. It doesn't matter how long the loop is, it will always stay 2. Of course, if we have more weirder connections, the average path length may increase over the tree. But typically, we have much more nodes which are close to each other in that tree than this off-tree constraint, which introduces a big error. Therefore, at least incrementally, we can say it's whatever we experience, it's smaller than log n, the average path length number of nodes. Just to give you an impression why it sounds sometimes a little bit odd that the size of your graph grows, but the average path length stays the same. The reason is that you typically don't have an arbitrary number of enclosures in there. Typically, have much more, say, regular traversals. Neighboring nodes are connected than big enclosures. That's the reason why this number is typically small. Okay. Oh yes, please.
About the slide.
Yeah, sure.
I'm now unsure what exactly is Olson's approach.
Okay, so this is the Olson's approach was the approach which I introduced before, which doesn't use the parameterization tree, but just use the lengths of the trajectory.
Okay.
And you can tweak that, but you can implement in a very optimized way that you end up with an n log n complexity. And the other approach is to be smaller. So this was kind of the way where you don't use a tree, but you just use a list. And just say between I and j, and you traverse the whole list always.
That's Olson.
This is what Olson's approach is, also parameterization. Okay, so this is just to give you an idea how this approach works. This is actually a sphere. Kind of a robot was walking on a virtual sphere, and this is how the approach actually performs the optimization. You can see it shakes a little bit around, especially with this shaking nature in every iteration. This results from the fact that you have this learning rate which decreases over time. You these constraints which contradict each other.
On that rotation we just saw at the very end, it looks like the sphere is rotating. Is that because the environment, the camera is rotating, or is that because the changes are slowly propagating?
That is because the changes are slowly propagating. I'm pretty sure. So it's quite a while ago that did this animation, but I think it was because of small rotations, not that the camera was moving. So, and this is also one of the problems that you can also see here in the graph, that what you typically have, so this is a log scale. So you have typically a dramatic decrease in error in the beginning, and then it takes very, very long until you really reach the minimum. And this is due to the learning rate, which gets smaller and smaller and smaller and smaller over time. And that's actually one of the problems you have for these gradient-based techniques, that they do not converge, typically do not converge as fast as Viscount-Newton-based methods. They have some other advantages, that they're typically rather robust to bad initial configurations, which they typically get less often stuck in local linear compared to Gaussian approaches. You can actually also see that if you have your sphere, this is the way you initialize it, you can actually generate arbitrary movements depending on how much area you introduce to the kind of motion of the virtual robot, and then you have 10 iterations, 50 and 300, you can actually see that the error goes down, but you especially see you have a dramatic decrease in error in the beginning and the first 50 iterations, and then the error decreases very, very slowly. This is this case.
Didn't want to interrupt you.
Yeah, no, go ahead.
But it looks like depending on how you initialize it,
yeah,
you end up either having a final error of 0.01 or having a final error of, well, slightly below 10.
That's completely right, because what you see in here is this was a small error which was added to the constraints, and bigger errors added to the constraints. Simply the constraints are more uncertain, so you end up with having bigger error values. If your observations have a higher error, you will have higher error values. So it's completely fine. So you never end up with an error 0 unless all your constraints are noise free. So you'll always have an error which remains. And this, actually, the error you obtained here reflects to the error you added to the individual constraint. So this is actually the error per constraint. This simply means, so here the error was probably 10 times higher than here, and here it was 10 times higher than there, approximately. So this, again, if you do this error minimization, this is always the case. As your observations are noisy, you will never reach the error value of 0, unless everything is perfect, which is very unlikely to be the case. So you can also show that it works in real time, in real environments. So this is an example. Actually, a very Stafford did while I was in the DPFL, so the DPFL campus. We also at that time built an autonomous car there with a couple of sensors here on top. You can drive around here, the campus of EPFL, there's some loop closures, some parking lots, and this is the initial configuration we obtained, and then we can actually optimize this so that this overlays nicely with the aerial image. So kind of small animation over here. You can see how the approach converges over time. Again, you see here, this is close to the conversion. You still see some small updates to it here until it really converges to the minimum error configuration. That actually suggests that it's a good idea, or this approach is actually well suited to use this as an initialization for Gauss-Newton-based techniques, because you dramatically reduce the error at the beginning. You're typically less sensitive to local minima compared to Gauss-Newton, but then they run a Gauss-Newton approach because simply converges much faster. So it actually makes sense. It's also one of the ways you can use this technique. You use it kind of to bootstrap your Gauss-Newton approach, and then do the final optimization with Gauss-Newton, because you're much faster. You're much faster in converging when you're close to the local minimum. Skip over a few things here. The only thing I wanted to show in here, actually the approach is pretty robust to the initial guess. So what you can see in here is, this was the example where you have this Intel dataset that you may still know from the beginning a few times. You kind of build 4 towers, where every floor is the Intel dataset. So it's kind of a mixture of the simulated dataset and real-world dataset. And if you initialize it kind of completely randomly around 0, distributed around 0, and you do the optimization, this kind of an intermediate result that you end up with, but even after a comparably small number of iterations, in this case 50, you actually are able to regenerate these towers. And this is something where in Gauss-Newton approach you would fail if you start with these initial guesses. And so it's kind of a nice thing in these approaches that you kind of locally rebuild the structure based on this parameterization tree, so it's a very local thing. So you locally rebuild the structure, and that's typically quite robust to bad visualizations. However, this approach also has some disadvantages. The first thing is that the translations and the rotations are optimized separately. So we decouple that. And if there is a correlation between both, this will be something which is completely ignored in this approach. So if you have a coupling between the rotation and the translation, that's something which is done suboptimally here. It requires roughly spherical covariances. This was the case for distributing the error in this completely case. It's actually pretty slow if you're close to the minimum in terms of convergence, and it doesn't provide you any covariance estimates. So it's really just only the most likely solution, because you can't build up, or don't build up this H matrix as in the Gauss-Newton, which you can invert and end up with the with having a covariance matrix. That's something which is actually missing here. There are other techniques where you can actually try to recover this covariances again, but typically a better approach is to run this as starting procedures for a few iterations and then switch to Gauss-Newton in case it doesn't even approach its problems to converge. So it's kind of one way for combining the advantages of 2 different techniques in here. So actually, it's an approach which works quite well for 2D as well as in 3D, but in 3D you need this slurp thing. In 2D, you can actually get rid of this slurp formulation and use it in an easier way. And these are actually things that I actually told you before. It's pretty robust to the initial configurations, can be used for initializations, and easily scales to millions of constraints, because it scales linearly with the number of constraints you have in your graph, but you can typically execute it easily for millions of constraints, and you don't have to invert any big matrices, as you may need to do it for the Gauss-Newton approach, especially if your matrix extends. There's sparse techniques, degenerating performance, and that's something which is not that critical in here. That's it. There's also literature, and they actually made the 2 approaches. So the approach which I referred to as the approach of Olson I told you before, which uses linear parameterization, and then a second approach which uses tree parameterization. Yes, please.
And about this bad initial configuration?
Yeah.
How would you get this situation in practice?
So I mean, these situations which look so dramatically bad, you typically don't have it at that scale. This was just an example to demonstrate how well that works. But it simply depends on the sensors you have in your platform. If you think, for example, about flying vehicles where you don't have an odometry sensor, and you have the issue that you may not be always able to match your observations in a very good way, then you can really end up in situations having very bad initial guesses. It simply depends on how much money you're willing to spend in terms of sensors to your platform. And second thing, what kind of platform do you have? Are you driving on very smooth grounds where you don't have any wheel slippage, or driving, let's say, outdoors through muddy environments, or even have lagged systems or flying systems? Then these issues of bad initial guesses are more relevant than for the extended wheel-based systems.
Can you add or delete constraints?
So, sorry, can I
add or delete constraints? So
what kind of constraints?
So like edge constraints. So I mean, could be if you say, okay, this is if you have some heuristics in saying whether a given landmark is actually the same landmark.
So I'm not fully sure what you mean with edge constraints. You mean data associations or uncertain data association?
Can I change data associations?
You can easily change data association if you know about that. That's not a problem.
No, within the iterations. Let's say I have.
You may need to rebuild the tree. So you probably need to. Maybe that you can, with an easy heuristic, fix a tree quite easily if only a small number of data associations change. But you may need to recompute your tree, which is not super costly. Typically, it involves computing a spanning tree approach. So like Pascal's algorithm, so it's not extraordinarily expensive, but you may need to recompute that if you want to change constraints very often. That maybe I haven't tried this, so I can just speculate on that. But you can definitely disable constraints, or also you can do what you would think. You can actually merge constraints if you're very certain about some block, and you have a whole block of constraints which gives you the same solution. You can merge them into one constraint. You can easily integrate that into that system, but it may involve recomputing, or you need to recompute your parameterization tree. Maybe there are ways for heuristically quickly updating it, but this I haven't explored. Okay. So, is there any further questions? Any further question? And then I suggest we make a 5-minute break and then continue with front ends and how one actually does data associations, and how to actually get these constraints. Okay, thank you.